Let's wait for a few minutes for others to join. Okay, we will start at 7. Sorry, we will start at 5. Uh, okay, so people are keep on joining. So let's wait for 1 minute more and then we will start. In the meantime, let me introduce myself to you. Um, I'm Prerak, and I will be taking these live sessions on Sundays. Okay, these live sessions are supposed to be of 2 hours. Okay, yeah, right. And these live sessions are meant to help you out during the course of invitation to topology. Um, so I will be having a few questions from the previous assignments of this course, um, and I will be solving a few of them problems from few of them, and uh, I might also add my problems from my side as well. Okay. Other than that, in any point of time, if you find anything if you are not able to understand anything, you can raise your hand, or you can type in chat box. Okay, or you can also interrupt me by unmuting yourself and ask question. Okay, so don't feel hesitate to ask question. This is informal session. Okay, let's not. But yeah, if you just be careful, you are going to be on YouTube, so so this recording is going to, I'm recording these sessions, so I will upload these sessions on YouTube. So yeah, so you can always go back to the these sessions online on YouTube, and then you can have a look at those. Okay. Okay, so yeah, I hope these slides, the presentation is visible to all of you, and I'm audible to all of you. If I'm not audible, please let me know now. If I'm not audible, if you can see that that I'm saying something but I'm not able, but you are not able to hear me, just raise hand. Okay. Okay, good. So then we can start. So before starting, let me ask you, do you guys have any questions that you want to discuss? Okay. So let me start with this very first question. Um, so question number one says that A be the collection of sets, then which of the followings are true? Okay. So first option says that uh, yeah, if X is in the union of all the subsets that is contained in A, this implies that X is in the collection for at least one of the A in the collection. Okay. Second option says giving the same element from the union of the subsets. This implies that X is in A for all A in A. Option C says that X is in the intersection. Okay, Rudra has already have the answer. D. Yes. So the option says that if X is in the intersection, then X is in A for all of A in A. Okay. Okay. So can Rudra, can you explain why did you say that D is correct, and why other options? Can you, and you need to give counter examples to all the other options as well, because these are wrong. Just quickly, if you can say something.
Yes, sir. Sir, the option B is definitely wrong because if X belongs to all the sets, then for X belonging to the union of all the sets, it can belong either in one or more.
Hmm.
And here it is saying in B option is saying that X belongs to all the sets. So B is incorrect.
Right.
C also, if X belongs to the intersection of A, then X will have to at least will have to be in all the sets, not just
Right.
anyone. So C is also incorrect. D and A I have confusion in, so I just put D because even A seems to be correct.
Yeah. So in this question, which of the followings are true? So it may happen that one more than one answer might be correct. Right. Okay. Yes, so option C is also correct, right? Because we need to careful understand the language as well. So it says at least one of the set has X. So in that way, C is also correct, because if it is in the it is in the intersection. That means this implies this thing. This is a very weaker statement to imply too, but it is true. Okay, for others, I hope you are very comfortable with understanding that option B is wrong. Because if X is in the union, then yeah, if X is in the union of all subsets of A, then X in the collection for all A in A. That's not going to be correct. So, for example, you can take a collection A to B. Okay, so let's say your collection A is singleton 1, singleton 2, singleton 1, 3, right? So that is your collection A. Okay. Now you now if condition B is true, then if X is in the union of all these A's, okay. So if you take the union of uh, the subsets of this will be what? So basically, this union of A from A in the collection will be a set containing 1, 2, 3, right? Saying that X is in this, or saying that X1 is in this union. Okay, so assuming that X is your 1, so saying that 1 is in this union, it does not imply that 1 is in the subset in the collection for all A in the collection, because you can find singleton 2 which does not contain 1, right? So B is obviously wrong. So this can be seen easily. Now we come back to the option A. Option A. Okay. So what is the definition of union? Set of all A in A for all A in the union. Okay. Or more appropriately, we can say it in this way: set of all X where X is in A for at least one of the A in the collection, right? So this is what the option A is saying. So it is true, right? There is nothing more in that. If X is in the union of the sets, then it has to be in one of the, at least in one of the subsets. Otherwise, X can't be in the union. Okay. If I look at option D also, as Rudra explained correctly, because X is in the intersection. So what does intersection say is that all the elements in the intersection, if there is an element in the intersection, then it has to be in all the subsets of A. Okay, collection A. So because of that, D is also correct. Now option C. Option C says if X is in the intersection, then X in the collection for at least one of the A. Okay, so this is not wrong, but this is true, right? X is at least in one of the A. But in this case, X is going to be in all of the subsets, but this doesn't make this statement wrong. Okay, because X in this intersection, so X is going to be in all of the subsets. Okay, so it is going to be at least in one of the subset. So it doesn't make this statement wrong. So this is also true. So we have three correct answer in this. And this is for B, counter example for B. Okay, so I hope this makes sense to every one of you. Any question on that? Okay, right. Yes. Now let's move on to question number two. Let X be a set and the A alpha be an indexed family of subsets. Okay, that is A alpha in X for each alpha in J. Okay, then which of the following are true? So the options are on the next page. Okay, so let me write down the options here itself. So the question will be complete here only. Option A, that union of A alpha is in X. Option B, X is contained inside the union of A alphas. Option C, that intersection that X is contained inside the intersection of A alpha. Option D, that X is that intersection of A alpha is contained inside um, X. Yeah, and these intersection containments are not proper, right? These are proper. Okay, these are not proper. Okay, then it is fine. Yeah, so these containments are not proper. These can be quality as well. Okay. So is this question clear? So we have given a set and we have given an index family of subsets of X. Okay. And what do we mean by subset? Subset is that A alpha, that, uh, yeah, the elements in A alpha are part of X. Okay. A alpha contains some of the elements of X in it, and it is arranged nicely, okay, by some indexing, and that indexing is given by the indexing set J. Okay, that is not of important task. That is just for indexing out them. Then which of the following statement is true? That their union is contained inside X, or X is contained inside their union, X is contained inside their intersection, or X is or intersection is contained inside X. A and D. Okay. Anybody else wants to guess? A and D options are correct, but do you think there can be any other option be that correct? That can be correct. B. Yes. Right. So yeah. Okay. So I will not ask Rudra to explain this one more time. I will explain it by myself. But uh, are others comfortable with the answer that Rudra is giving? That the options are correct. That A, B, D are correct. Okay. Let us first focus that why C is going to be wrong. Okay, so what does C say? C says that the X is contained inside the intersection of A alphas. Okay, so now let us come back to the definition of the intersection. Intersection of, yeah, actually, B is also will also not be correct. Okay, there is a reason for that. In some cases, you can say that B X can be correct, but B is no going to be wrong. So only A and D is going to be correct. Okay. Now let us come back to the definition of A alpha. Okay, intersection of A alpha is all X all x such that x is contained in A alpha for all alpha in J. Okay, only those x which is contained in all of A alphas. That is the intersection. Now, we want to know whether it is a subset of x or not. Okay, that is one thing. Another thing is that x is contained inside. This is option number D, that it is contained inside x, and this is option number C, that it contains x. So let us first look at that it does it contains x or not. So we will give an example to that. Again, we come back to the previous collection. Now let us take our x to be 1, 2, 3, 4. Okay, and let's say I have a finite indexing. A1 is singleton 1, A2 is singleton 1, 2, A3 is singleton 1, 2, 3. Okay, A4 is uh, yeah, an is equal to a3 for n greater than equal to 3, right? So I have this indexing to be given. Now if I take the intersection of these ai, now let us look at the intersection of a1, a2, a3. That is what the intersection of this would mean in our case, right? So this will be what? This will be singleton 1 only, right? Now you can clearly see that x does not contain in 1, because x is a bigger set, 1, 2, 3, 4, right? And it is not contained inside 1. So this implies that C is not true, because I am able to find out an counter example to that proposition. Okay, so this thing is not true, because this is an example, working example for that. Now, what about the other options? What about B? So, what about AD? AD, first let us look at AD, why they are true. So, I will give you a mathematical proof. Okay. So, first let us prove this. Why union of A alphas is contained inside X. So, we know that A alpha is contained inside X for all alpha in J, contained or equal to B. For all alpha in J, right? Now, hmm, yeah. So, what is the union? Union is, now let's look at the definition of union. So, union is all x such that x is in A alpha for at least one alpha in J, right? That is what the definition is. So, now if I take an x inside this union, so I need to prove that this is contained inside x as well, in order to show that this is a subset of x. Okay, or in general I can say that if I want to prove, so in general if you want to prove that B is a subset of A or B is a subset of D, then it is equivalent to show that x, if x is contained inside B, then it is contained inside D. Okay, so let me write it better. For all x, because these for all x in B, we will get x in D. Okay, So these two things are, so this is how we show that B is a subset of D. This is, so this is what I'm using over here as well. I want to show that union is contained inside X. So I need to show if I take an element from the union, it has to be an element of X. So now, since element of union means by definition that X is in A alpha for some alpha in J, right? And A alpha, and this implies that because A alpha is a subset of X, so A alpha is contained inside X. So this implies that X is in X. So this is the proof. So this implies that union is a subset of X. Similarly, for intersection, you can show that. I leave the proof for intersection for you guys to figure out, but the proof will work on the similar line. You need to use this similar formulation, this, in order to show that. Mathematically, if you want to show how to show this, so this is what you need to use. So let me give you a hint. Yeah, so intersection of A alpha. Again, we will take an element from the intersection. And now this implies that X is in all of, is in A alpha for all alpha in J, right? But we only need one, X needs to be only in one A alpha in order to show that it is a subset, right? Because that's what we see earlier. And it is in all of A alphas. And we know that A alpha are subsets of X. So now you know that X is in X. So this is also done. But this is not detailed proof. This is a detailed proof only, but you need to, yeah, you must be able to you must be able to understand each and every detail of it. Okay, so I have said why uh, D is true, why A is true, why B is false. I haven't said by B is, I've said C is false. I haven't said that by B is also false. So I need to give a counter example where B can be false, right? Yes. So, so for example, take your X to be Z, okay, and take your A alpha, define your A alpha to be this way. Yeah, singleton J only for indexing set for J in natural numbers, right? So if you take that, so we all know that what Z is 0 plus 1 minus 1 minus 2 2 and so on and so forth, right? This is what Z is. We all know what AJ is also, because A1 is what? Singleton 1. A mine A2 is what? Singleton 2. We need to be careful here because the indexing set J is coming from natural numbers only. So we won't get A minus and A0 because minus 1 and 0 are not element of natural number. So we won't get that. We only get the positive integers. Okay. Right. Now if you take this collection and you take their union as well. So you take the union of AJs. What will you get? You will get singleton 1 union with singleton 2, union with singleton 3, and so on and so forth. So in the end, you will get, because it's a union of all positive integers or union of all whole numbers, so you will get natural number itself. So this union is nothing but the natural numbers, which is which does not contain z. That we all also know that natural number does not contain z, because zero is not there and minus integers are also not there. Natural number only contains positive integers. So so this is an example why v is false. So a is true, c is true, and d is also. Oh, sorry. Um, yeah, a, d are true, b, c are false. Yes, Rudra.
Sir, when we say that when we say that we are looking at the subsets of X in terms of A1, A2, A3, don't we mean that we are actually parting the set X into J? So that means a
No, no,
union
no,
of.
no, no, no. That's what not. That's what I thought earlier as well, but that's not given in the statement. So the statement is pretty weak in that sense. Look at the statement of the uh, question. It just says that AJs are the index family of subsets of X. It doesn't give you anything else. It doesn't say their union has to be, their union contains X. So that is, it's not a partitioning. It's not a partition of X. Yeah,
Okay, so thank you, sir.
yeah. Good point. Okay, so yeah. Sorry. Sorry. Okay, any question on the previous question? Question number two. Any question on question number two? Anyone? Okay. So I'm skipping a bit in between. If we find time in the end, I will come back to these questions as well. Now let us look at these relations and functions. Okay. Hmm. Okay. So we say a function f from a to b is a relation that is a subset of a cross b. So a cross b is the Cartesian product of a and b. You guys have already seen in this first week's lectures. And I think you have also gone through the definition of function, but okay. Existence of image. For each a in a, there exists a b in b. Okay, you need to be careful here with the definition. Uh, for each a in a, there exists a b in b, such that ab, the tuple ab, is in f. And uniqueness of the image: if ab is in f and ab prime is in f, then b must be equal to b prime. Okay, so this is what the definition of a function. It simply means that if you draw points of a here and if you draw points of b here, then for each point in a, there has to be an image. Okay, it can't be like there is no image to it. Okay, there has to be an image in order to have a function. And A can't go to two images. That is the second point. That it has to have a unique image. Okay. So first of all, A need to have an image, and the second point is that it has to be unique. Okay. So if this is clear, now let's move on to this question. Which of the following are true? This question number 9. So if A is non-empty but B is empty, then there is no function from A to B. If A is empty, B is non-empty, then there exists a function from A to B. If A is empty, B is non-empty, then there is no function from A to B, which is yeah. So these two options are like, if one of them is positive, the other has to be negative. Uh, and similarly, AD is also like that. If one of them is true, then other has to be false. So there can maximum be two options be correct. Okay, there can't be more than two options be correct. Right. Okay. Now, why is option A is correct? So, in order to say that why option A is correct, you need to understand the definition then. Okay. So, is anyone want to answer this? Okay. A and C. Anyone else? Guys, you can guess any of the options. Uh, so there has to be some intuition coming in your head. You just go with it and answer the question. There is no exam going on. So you can answer whatever, but you need to have some reasoning behind it. Maybe correct or wrong. That is fine. But yeah. Like, I would appreciate if other also will participate, like Rudra. So mm. Okay. Anyways, so so Rudra answer like A and C are the correct option. Okay, now let's explore. So because A is non-empty, so there has to be an element in A. Because A is non-empty, there has to be an element in A. And B is empty. So so A has an element. I will denote it by a dot, and B has no element, so there is no dot. Okay. So B is empty. Now for this dot, sorry, yeah. Now for this dot, looking at the definition of the function, there has to be an image to that dot. Okay. And that dot has to be unique as well. But there is no dot in B to connect to, right? There is no element in B which can be an image of A. Okay. So there can't be any function. So the existence of image is not satisfied in option A, right? So there is no image of A. So for an element in A, you can't find an image in B. Okay. So this is the so you yeah. So existence is not there. Existence of image is not there for option A. So this is false. Sorry. So there is no function from A to B, right? So this is true. That's what this option says. Okay. Is this clear to everyone? Now for option B, I have given that A is empty. Okay. Now A is empty and B is non-empty. So A has no function, no element in it. B may have elements, it doesn't matter. Now can there be a function? So let us look at the first condition, existence of image. It says that for each A in A, element in A, there exists a B in B, such that AB is in F, right? But if there is no A in A, okay, we don't need to worry about the image. Okay, we don't need to worry about the image set, whether the image is there or not. Okay, so it says whenever there is an element in A, you need to have an image. But when there is no element in A, you don't need to worry about the image element. Okay, so the existence is vacuously true in this case. Okay, so there can be a function from empty set to any non-empty set. Then that function will do nothing because there is no element to act on. Okay, there is no element to function on, right? So this statement is also true. Now, as I said earlier also, that A and D are uh, complement answer to each other. So if one of them is true, then other has to be false. And similarly, B and C were also complement answer. So if B is true, then C has to be false. So since A is true, D is false, and B is true, so C is false. Is this solution fine to everyone? Yes, Manda.
Sir, by this logic, by the uniqueness of an image, for option B, then every element of that set B should be equal.
So basically, you are not assigning any element to the image. That is what I'm saying. Because whenever you have an element in the domain, you assign an image to it. But when you don't have, you don't need to assign any image, any element to it, right? That is what the existence says. Whenever you have an element in A, you need to assign an image element. So when I don't have any, I don't need to assign any, right? It says for each
Okay, sir.
A in A. Um, yeah. So there is there cannot be any assignment in that way. Good question. Okay. Anybody else have anything to ask? Right. Okay. There is no question, and let's move on to question number 10. Okay. Yeah. So question number 10 says which of the following statement are true? Right. Which of the following statement are true? Uh, Option A says if A is empty set, B is non-empty, then any function from A to B is injective. If A is empty, B is non-empty, then any function from A to B is surjective. If A is empty, B is empty, then any function is bijective. And if A is empty, B is non-empty, then there is no bijection from uh, A to B. Right. So I assume that all of you know the definition of injective functions, bijective functions, and surjective functions. So let me quickly recall as well. Injective means, uh, yeah. So I will let me again use the dots. So we know that every element of A can go to a single element in B. Okay, it can't go to two elements in B. Okay, but elements in A can go to one, two elements in A can go to single element in B. Okay, like this, like A and B are going to the same element, same dot in B. Okay, so when we prevent this to happen, okay, so how do we prevent? So when we say, mm, right, so when we say that, yeah, no two elements of A goes to a single element in B, then it is injective function. For surjective, if there is no element in B left out to be image. Okay, so in other words, uh, every point in B is an image of a point in A, right? Bijective means that it is injective also, and it is the map is surjective also and injective also, right? So now it is clear. So now option number A. Okay, any guesses in this question? Any guesses by you guys? Okay, AC. We got one guess. What about others? Yes. Namita has given another guess, which is ACD. Okay, good. So, can I ask Namita now? Why did you say D is also correct? Because AC Rudra also mentioned, so D is also correct. Why did you say? Can you explain that?
So because in D the it's not onto, so therefore bijection doesn't hold. Therefore the statement becomes true for D.
Okay, right. Um, okay, I hope others understood that. Okay, now let me explain why A, C, D are correct. So, so A is true because there is no element in A, so it is not mapped to, it is not assigned to any element in B. So that's why uh, no two, so two elements in A need not to go to the same element, which is vacuously true because there is no element in A. So it is injective by triviality. Similarly, B also, B, since in B A doesn't have any element in it, so it there can't be any surjective map, right? So there is no way possible that you can have a surjective map from A to B. So uh, this is also trivial. This is false. Now, when you have empty map, empty set and empty set on the both side, and the domain also in the range also, and you are asked for a bijective map, right? So yeah, because there is no element in A, okay, it can't be mapped to any element in B. And since there is B in B, there is no element to be mapped to. Uh, so every element in B is also mapped in this way. And since A doesn't have uh, any element, so no two elements are going to the same element as well. So it is injective also. And because B doesn't have any element in it, so it is surjective also. So in this way, it is uh, bijective. So it is injective because of the A. The C map is injective because of the A, and it is surjective because B is empty. Okay, so this is also true. Now, why D is true, as Namita mentioned, because A, uh, yeah, because there can't be any surjection, right? Uh, yeah, you can have an injection, but you can't have a surjection from A to non-empty set, right? So because of that reason, this is also false. This is also true. So there is no bijection. So it is also true. Correct. Good. I hope this is clear to all of you because you guys only answer this question. Okay. From for next questions from 11 to 14, these questions A and B are non-empty sets and F is a function. Okay. Now let's move on to these questions. So question number 11 says that which of the following are true? Which of the following are true for a non-empty set subset? A, F inverse F of A naught is equal to A naught always holds. B, F inverse of F A naught is contained inside A naught always holds. A naught is contained inside F inverse of A naught always holds, and D, A naught is equal to F inverse of F A naught if F is surjective. Okay, is the question clear to all of you? Right. Okay. Now my question is which one always holds? Yeah. What are the correct answers? Any guesses? Oh, sorry. This is uh, injective. Yeah, that's what I was thinking. Right. If A is true, then B is also true, right? Uh, C will automatically be true. Yeah, if A holds, then A, B, C are true, right? But yeah, now the question is if A true. So A is true only in the condition when, uh, yeah. So A and D are related in that way. So if F is injective, uh, then only, yeah. Okay, okay, okay. So now let's understand. So this thing is not true in general. That F inverse of F of A naught is equal to A naught. Okay, because of the simple reason you can think of is that if you take a you can construct a simple function 1 2 3 going to 3 4, right? Now you, yeah, now these mapping defines the map. So it says that f of 1 is equal to f of 3. This is your A, this is your B. F of A is equal, f of 1 is equal to f of 3, f of 2 is equal to f of 4, f of 3 is equal to f of 4. Okay, and your A naught is, let's say, 1 and 2. So we know that f of A naught is 3 4. But if you take the pre-image of this, pre-image of 3 comma 4, so what are the pre-images of 3 comma 4? It is 1 2 3, because 4 is a common image of 2 and 3. Okay, so the pre-image will be 1 2 3, right? Which is not equal to A naught, but it does contain A naught. Okay, right? So yeah, from this example you can notice that A is false. That's what only you can say, that A is false, and it gives you hint that C might be true. Okay, now let us look at option B. Option B says, yeah, option B says f inverse of f of A naught is contained inside A naught. Okay, yeah, so this is an example for B also, in which it is not contained inside A naught, right? So this also gives you counter example that B is false. Okay, what was A naught? A naught is contained inside this, but A naught does not contain a bigger side 1 2 3, right? So this is also counter example to B. So B is also false. Now let us look at option C and D. Okay, is this clear that option B and A are wrong? Is this clear? Okay. Um, You guys can thumbs up or something like that. You can say okay or something, in chat box if you find that the options are, if you comfortable whatever I'm saying. Okay. Uh, yeah. So option C and D, that's what remaining to focus on. And this example is not a contradiction to option C, and it hints that option C might be correct. So now let us look at that. So if you take x in a naught, so because I want to prove that it is containment, so I will just use the containment. So let's say x is in a naught. I want to show that x is also in f inverse of f of a naught, right? So so let y is equal to f of x. So y is in f of a naught, right? Now what are the pre-images of f of a naught? Right. Okay. So y is in f of a naught, and clearly from this we can see that x is also in the one of the pre-image of a naught. Yeah. So yeah, now let us look at this set f inverse of y, which is the set of all a in a naught, such that f of a, sorry, yeah, it's a set of all a in a such that f of a is equal to y, right? And and we know that um, x belongs to f of y because of this assumption. So let's call that by 1, by 1, and the definition of f inverse of y, right? So right, and now f inverse of y, because y is nothing but an element of f inverse of x. So okay, and f inverse of y contained inside f inverse of f of a naught. Okay, now what is this set? This is because the definition of this set, which is set of all elements a in a, such that a such that f of a is in the image of a naught. Okay, so from this we can say that, yeah, f of y inverse is contained inside this bigger set, or from this definition itself you can say that x is in the image of, yeah. So since we can say this, and now x is in this, so this implies that x is in f inverse of f of a naught, right? So this whole thing implies that a naught is contained inside f inverse of f of a naught. Okay, I think I have made it more tricky than usual. There can be a shorter version of this. You just need to look at the definition of this thing, which is f inverse of f of a naught is set of all a in a, which I just wrote it over here, that f of a is contained inside f of a naught, right? And y is in this set because since y is f of x, right? So this implies that y, that's why y is in f inverse of f of a naught, Oh, sorry. Yeah, y, since y is equal to this, y is equal to this, so this implies that x is in uh, f inverse of x naught, right? So this implies that a naught is contained inside. Yeah. So this is a shorter version of the proof. This is unusually bigger version of the proof. I don't know why I did that, but okay. So this is shorter proof. Okay. Yeah, unusually bigger proof. You can skip this part and just have a look at this. Okay. So this says that option C is true. Any doubt in this proof? Shorter proof. You can ignore the bigger proof. Okay. No doubt. Then we can discuss option D as well. So option D says that a naught is equal to this if f is injective. Okay. So you can so in this example you can clearly see that the problem here was that if I take the pre-image of a naught, f of a naught, so there can be an element with whose pre-image is of two elements, right? And so that is what the obstruction in order to make this set is equal to a naught. Okay, this is what we can observe from this. So if I get rid of this obstruction, which is explicitly saying that if I make my function to be injective, if I say that no element in B has more than one pre-image, okay, if I say that, then I will get the equality. Okay, this is intuitive idea. But if I want to write it down explicitly, so I want option D, that a naught is equal to f inverse of f of a naught if f is injective. Okay, so one part we have shown that a naught is contained inside f of a naught. This is shown. Now we look at the other part, that f inverse of f of a naught is contained inside a naught. Okay, this is what we are going to interested in showing. Okay, so now let's take, let x be in the, let x be in this pre-image. Okay, so that means what? Now what is the definition of f of a naught? Definition was set of all a in a such that a f of a is contained inside f of a naught, right? Okay, so that means f of x is contained inside f of a naught. Okay, now what does this mean, that f of x is contained inside f of a naught? It means that there is another element in a naught whose image matches with the f of x image, right? So there is a in a naught such that f of x is equal to f of a, right? Or yeah, yes, this is true. Okay, because f of x is in f of a naught. If x does not belongs to a naught, then there has to be a in a naught whose image matches with that f of x. Okay. Now since f is injective, it forces that a has to be x has to be a, right? Implying that x is in a naught. So we get that f inverse of f of a naught is contained inside a naught. Okay. So we have already seen this from option C, and this is we have proved just now. So using these two inequality, we can say that a naught is equal to pre-image of f of a naught if f is injective. Okay. So is this proof clear to everyone?
Yes.
Good. What about others? So this is true. So option C and D are correct. Okay. Now let's move on to discuss another question. Question number 12. Which of the followings are true for a non-empty set B naught in B? Option A, f f of f inverse of B naught is equal to B naught, always holds. Option B, B naught is equal to hmm, this is again the similar question. Um, Option C, f inverse of f of B naught contained inside B naught. Option D, sorry, inverse is an inside this time. Okay. B naught is equal to f of f inverse of B naught. This always holds option C as well. And option D, if B naught, sorry, if f is surjective. Right. Okay, so I hope this question is clear to all of you. I will give a few minutes for you to think about this question and then I will proceed. Okay. You can let me know your guesses as well. Okay, C and D. What about others? Any other guesses from any one of you? Mm. Okay. Um, yeah, option C and D are correct. So let me start with giving counter examples to A and B. Why A and B does not are not true. Okay. So again I will use the dotted notation because it is simpler. We can get counter examples in finite sets as well in only. So we don't need to look at the arbitrary long examples. Okay. Yeah, so in this case, let us assume that this is my B naught. So clearly B naught is a subset of B, right? And my function f is a constant function because image of uh, A is a constant. Okay, every element is going to a same element in B. So it is a constant function. This constant function. Right. And now you just apply condition one. So B naught consists of these 3 points, but F inverse of B is whole A, right? And uh, if you apply F on A, you get only this singleton point. Okay. So this is just singleton. Let's call that singleton to be some P point. You get P, singleton P, which is contained inside B naught, but it is not whole. Okay. So so this is false. Similarly, yeah, B is also false because you can see that this implies that F inverse of B naught uh, contains B naught, right? So option B is also wrong, is also false. Okay. Now, option C and D, let us now look at the proof of option C and D. So option C says f inverse, oh sorry, f of f inverse of B naught, yeah, contained inside B naught. Okay. So again, I will use the same set theoretic notation and conventions. So start with let x be in this uh, set. Okay. So what does this mean? That x is image of some element of y, where f of y is in B naught. Okay. Or such that. This is correct, right? So you start with any point, the pre-images of points in B naught, you will get more points, and then now you look at the images of uh, those thing. Okay, so that's what I'm saying, that if you take any point in this, so this point is going to some f of y, where y is in f inverse of B naught. So let me write it like that: f is y is in f inverse of B naught, which is equivalent to say that f of y is in B naught, right? Now it is fine. Hmm. Okay, so this implies clearly that x is in B naught because of this whole expansion. X is equal to f of y, and f of y is in B naught, so x is in B naught, right? So this implies that f of f inverse of B naught is contained inside B naught. Okay, so this says that C is true. Now let us look at the D part. It says that f inverse of this is equal to B naught if f is surjective, right? So for this part, we need to say that this is contained inside B naught, that we have already shown. So this is done. The other part that we need to say is that B contained inside f of f inverse of B naught, right? So now let us prove this part, and we have the uh, extra assumption that f is surjective. So again, let us start with a point in B naught, x. Okay, let x in B naught, and now what is the definition of f inverse of f of B naught? It is set of all points in B, okay, such that f is equal to f of y, and y and f of y is in B naught. right? Now we know that f this set f of f inverse of b naught is already contained inside b naught. So what are the remaining values to show that uh, this this is already a subset of b naught? So if we can show that whatever is remaining, okay, so if we can say that this complement of this complement of f inverse of b naught in b naught, if I subtract it out, so whatever the elements are remaining are also the images, uh, yeah, is empty set. If I can show that, then also I'm done, right? And this can be shown by saying that f is surjective. There is no other element in this. So suppose um, that means by y is in b naught, but by y is not in, okay. Now what is this? This is, yeah. Now what does this mean? This means that um, yeah, so y is not in f inverse of b naught. It means that this element is being left out, okay, uh, in the image of b naught, right? So this implies, right, there is no a in fp naught because being in this image, meaning that it is a collection, it is a subset of b, says that a is equal to image of some f of y, where y is in b naught, okay. Yeah, y is in the pre-image of, uh y is in the pre-image of b naught, right? So if y is not in this, mm, just let me think for a moment. Right. Yes, Rudra.
Sir, then if our f function is not surjective, then f
Hmm.
inverse, that is a function from B to A, will not exist. So that alone should
No,
prove it.
no. F inverse function is not the inverse function. It is the preimage. It is a notation. It is not a function. F inverse, F inverse of B naught. So it is a subset of A. In order to exist
Okay,
an
sir.
inverse function, a function needs to be injective. That is not the argument
Yeah.
over here. The argument over here is that there is no point in B which is left out. Okay, so there is no point in B naught that is left out. That is what the argument over here. I just want to show that using the mathematicals, using the logical deduction, that there is no element in B naught that is lefting out. Just give me a moment. I will give an argument. Hmm. Hmm. Okay, let me rub this all out. Cool. Hmm. Yes. So since x is in B naught, if I start with any point x in B naught, and now if I consider this set f inverse of x, it will be a subset in A. Okay, it is the selection of all. Uh, yeah, because x is in B naught. So let me start with this part. Let me rub this all out as well. Yes. So since x is in B naught, this implies that f inverse of x is contained inside f inverse of B naught, right? Because this is the by definition. F inverse of B naught is collection of all preimages of every element in B naught, right? And now this is f inverse of x. And if I take, yes, and if I take right, and if I take the image of this in simple words, um, now let A is in f inverse of x. Okay, so this implies that A is in f inverse of B naught. Okay, right. Now f of A, it will be contained inside f of B naught. And now what is f of a. F of a is x. Right. So this is what completes the proof. Now, where I'm using the surjectivity, you may ask. I'm using surjectivity um, here only. Okay. When I'm saying that, given a x in B naught, there exists a pre-image. Okay. So why f of this is non-empty? Because f is surjective. Okay. That is where I'm using surjectivity. Uh, yes. So A exists. So there is such A who is in f inverse of x. And when there is such A, you can just apply the definition and then you will get this. So this completes the proof of f inverse of B naught is contained is equal to B naught. Okay. So let me go through this proof once again. Yeah. So in order to show this equality, we need to show that the image of f inverse of B naught is contained inside B naught. That is the first part. Second part is that B naught also contained inside f of f inverse of B naught. Okay. We have already shown the first part. Now we are only left to show the second part of it. So we start with any arbitrary. Uh, so we start with any arbitrary element x in B naught. Okay, and we consider its pre-image. Okay, and we consider this pre-image. Now, yes, and we consider this pre-image. Now, because this pre-image of x can be empty also. Okay, there is no possibility that there will be an element in this pre-image. It can be empty as well. For example, in this case, if you take pre-image of this particular element of this constant function, then its pre-image is empty set. Okay, so it can be empty, but what it is preventing here to be not empty, that is precisely the surjectivity. Surjectivity ensures that every x in B naught or every x in B has a pre-image. Okay, so f inverse of x is non-empty set. That is what the important point over here is. And because uh, since f inverse of x is non-empty, this implies there exists a in f inverse of x, that is a is equal to, that is a f of x is sorry, f of a is equal to x. And now because of this, uh, a belongs to f inverse of b naught, and if you apply f of a to it, it will belong to the f inverse of b naught. And what is f of a? F of a is nothing but x, so x belongs to this set, and this gives us the equality. Okay, the other side containment as well, and then the equality. So is this clear, this argument clear to you, all of you guys? I'm sorry that I took more time in this, but yeah, I just want to come up with a very nice explanation to you. Okay, anyways, is this clear? Is this solution clear to all of you?
Yes, sir.
Good. So this is true, and this is also true. So correct options are C and D. Right. Okay, I will discuss one more question and then we can stop. Okay, so there is this question number 16. Let A be non-empty set and B is a subset of A. Which of the followings are true? A, if A is finite, then B is finite. B option, if B is finite, then A is finite. Option C, if B is infinite, then A is infinite. Option D, if A is infinite, then B is infinite. Okay, A and C. Mm, right, that is correct. So there's a so let me start with giving a counterexample to B and D, and then I will come to this explanation. So B is says that B is finite, then A is finite. That need not to be true. You can take there can be a finite subset to any infinite subset. Okay, and to be precise, you can take A to be natural number set and B to be just the one singleton one. Okay, so clearly B is finite set because it is cardinality is one, and N is a natural number set. It's countable set. It's a infinite set. Okay, so B uh, is finite, but A is not finite. Okay, so this is false. B being finiteness of B does not imply the finiteness of A. Similarly, in D also, if A is infinite, then B is infinite. It need not to be true. For example, again, this example works. If you take the natural numbers and you take the singleton B, a singleton 1 to be the subset B of A. Okay. So, infiniteness of A does not imply the infiniteness of B. So, this is also false. For A and C, if A is finite, then subset B is also finite. Why? Because if I assume that B is infinite, okay, if I assume that B is infinite, uh, so by definition of subsets, every element in B has to be an element in A as well. So if there are infinitely many elements in B, so there has to be infinitely many elements in A also, which contradicts to the fact that A is finite. So Uh, yeah, so B has to be finite. So this is true. Similarly for C, we can again use the contradiction. Um, right. We can again use the contradiction. Uh, if B is infinite, then A is infinite. Assume that A is finite. Okay. So if I assume that A is finite, so by option A, if A is finite, then B has to be finite. So it implies that B has to be finite, but B is given to be infinite set. So A can't be finite. So A has to be infinite. So this is also true. Okay. Right. Yeah. Any question in this? Is this question clear to you?
Yes, sir.
Good. Okay, so I have a very quick question again, like this one. Let me write down that as well. So it is a logical question. Let P and Q be logical statements. Again, you need to find out which of the following always holds. Which always holds. Option A, P implying Q. Does it also imply that? Hmm. Does it imply? Uh, yeah, not P uh, implying not Q. Similarly, when P implying Q, not Q implying not P, Q implying P, not P implying not Q. Okay, Q implying P, not Q implying not P. Okay, so I just need to guess you which one of this is going to be correct. And since this is a logical statement direct question, assume that all of you must be able to guess the answer. Right, that's counter positive, right? So such statements, such arguments is called counter positive. That's what I use in actually this question in proving in saying that A is yeah, in saying that A is true. I use this even in saying C is true. I use that counter positive statement. Okay. Sorry, I use contradiction. I assume I contradicted the statement. Uh, you can treat that as counter positive as well. Okay, but yeah. Yes, B and C are the correct options. Uh, P implying Q does not imply that not P is equal to implying not Q. P implying Q implies that not Q equal to not P. That is true. This is also true. You just need to switch the role of P and Q, and this is false. This is also false. Okay, guys. Yeah. So we stop here. If you guys have any question, you can ask me, or we can discuss it in the next session as well. Some Sunday, same time, 5 to 7.
Okay, sir. Thank you, sir.
Yeah, you're welcome. You guys can leave now if you want. Yeah.
Bye, sir. Thank you, sir.
Yeah. Bye. See you next week.